Well, we're up to 60, expecting a few more. That's a pretty good audience to kick this off. I'm Alan Taub, and I am the director of our new electric vehicle center at the University of Michigan. We were actually just finished our second year anniversary. We were founded with a grant from the state of Michigan, and we're working with companies on technology, education, workforce development, as well as improving the facilities to do electric vehicle research at U of M. Today, I'm pleased to announce a colleague who I worked closely with when I was at GM and now getting a chance to interact with again in the Electric Vehicle Center, Madhu Raghavan. Madhu is a senior technical fellow and lab group manager at GM R&D. His responsibilities range, from the full range of electric propulsion systems, megawatt charging, chemistry mixing for batteries, novel energy system architectures. He has over 300 patents and is a fellow of ASME and SAE, as well as recently been elected to the National Academy of Engineering. He earned his bachelor's degree from IIT-Bombay and MS and Ph.D. from Stanford, followed with finally an MBA from University of Michigan. Uh, so with this, I'd like to turn it over to Madhu. What we ask people to do is hold their questions until the end, but please, as soon as you have them, put them in chat. At the end of the talk, Jamie Ratcliffe, our communications director, will manage the Q&A. So Madhu, I will turn it over to you.
Thank you, Professor Taub. Can you hear me?
Yes.
Oh, okay, perfect. And Jamie, can I share, or are you going to share anything, or can I go ahead and share?
Go ahead and share.
Okay, thank you. Okay. Am I on? Can you see my screen? Full screen?
Yes.
Okay, perfect. Thank you. So thanks again, Professor Taub. This is a real honor because I sat through the other third sessions and they were awesome. So I'm so happy to have this opportunity to be able to add to the conversation, add to the discussion. I do have two screens open, so if you folks are putting questions in the chat, we'll stop and take some questions every so often. So when Professor Taub and team, what's happening out there? Let's see. Yeah, when they asked me to do this, what are you going to talk about? So we said, well, let's talk about challenges in electrification. I started to put together this list, and I pretty soon realized that this is common to all of us, right? As propulsion researchers in this business, whether it's industry, academia, suppliers, or whoever. And so the number one thing we're looking at is pack energy density. How do you get sort of more energy into the vehicle? Because you have limited, package volume. The other trade-off or contradiction that we often face is this power versus energy. So when you design for power, you don't get enough energy. When you focus on energy, you don't get enough power. So getting that, the exact right mix is a challenge, and then it varies from application to application. So you end up sort of looking at bespoke cells for each application. So that's a bit of a challenge. Safety is a big issue, right? Because the more energy you pack into the res, the worst the situation is if something untoward were to happen, like a thermal event or whatever. So big focus on safety, huge focus on efficiency. So if you and I have the same pack, but your vehicle is more efficient, it's going to go further, right? So there's a lot of focus on vehicle efficiency. And then once you get to the destination, you'd like to charge as fast as gas, because right now charging is much slower. And I threw in cost because normally in my work meetings, cost is right at the top, because if you don't meet cost, you don't have a product, you don't have marketable products, and then the rest doesn't matter, right? But for this discussion, I didn't want to start with cost and everybody will be rolling their eyes, because that's such a tight constraint that it might limit creativity and innovation. So I've kind of left it there. It's hovering in the background, all right, but we have to sort of pay attention to it, even if we're focused on the other things. Now, this is such a rich subject. It's probably the best time in one's life to be like a propulsion electrification researcher, because the situation is perfect, right? You got the challenges, you got all the geopolitical issues, you have competition and so on. And so I could talk about this stuff for like 6 hours, but just given the time limit, I'm going to focus on the three blue arrows: the power versus energy, getting more efficiency out of the drivetrain, and then fast charging. So before I leap into the technical details, I wanted to take 30 seconds to say thank you to my employer. So this is where I work. This is the General Motors R&D Center in the beautiful Tech Center in Warren, Michigan. And that's our building. So my office is somewhere up on the third floor overlooking a really nice lake with fountains and whatnot. And this is a super place because you have experts in all the different domains. It's sort of like just like a university, but with sort of an applied focus. This was perhaps the world's first automotive research organization, founded by Boss Kettering, and it's a totally awesome place. I've been there 36 years, and it just feels like time went like that, like a snap of my fingers. Here's another shot of that building. And what I wanted to show in this picture is all the other locations we have and how we interact, right? So we do all our ideation here. Can you see my mouse? Uh, you guys can see my mouse?
Yes, yes.
Okay, good. So we do all our ideation here, and then a lot of the lab testing, the dynamometers and so on, we do that in our Pontiac facility. So you start with idea, take it to the lab, do the subsystem testing, and then we do vehicle integration in Milford. So that's where kind of the new subsystems come into a vehicle. Then we take it out on the track and you do high-speed testing or whatever it is. So it's a real fun place. Milford is awesome. And then we have our smart people sitting in Sunnyvale and Herzliya, Israel. They do the AI machine learning. A lot of the autonomous, software and controls and so on come from those teams. We also have a facility in Shanghai where we work to kind of the local requirements, and also it allows us to work with the local suppliers there because they're really awesome. I mean, they're competitive and they're moving super fast. And then we get all our high-tech sensors and materials out of the HRL Hughes Research Lab in Malibu, and so that's how it all comes together. But I would say this is the center of gravity of our activities. And then as far as my group, we're 8 researchers. It's called the Battery and System Architecture Group, all PhDs from different disciplines. And we have shown here a suite of tools. So we can do the entire energy system modeling. So a couple of weeks ago, I was in Professor Jing Tang's energy systems class. I gave a lecture, and we look at getting the fuel out of the ground or the photons from the sun or whatever the source is, and we can model the entire pathway to the gas tank or to like the electrical charge station. So you can look at the economics, the efficiency, et cetera, et cetera, et cetera, by region, and by work stream. We can look at that in great detail. So that's part of our work. I'd say most of our work is actually what happens on the vehicle. So we have propulsion architecture modeling tools like the screenshot shown here, where you can model an entire vehicle. You can put an aero, you can put tires, mass, novel engine technologies. Now it's been mostly batteries, motors, power electronics, transmissions, and so on. And at a system level, you can do synthesis and optimization. So these tools are super powerful. And the reason I'm showing you this is all our new ideas, all the new ideation, it goes through this set of tools. And then if it looks good, then we start to get busy and then we start to build prototypes like the stuff that's shown here. So I've done like, I don't know, maybe 70 projects in the 36 years I've been with GM. So I just picked out a few iconic ones that I think you will like, but I'm not going to talk about all of them, but this is just some eye candy just to give you a feel for the kind of stuff we do. So here's an 800-volt 1 megawatt pack that we built in the 2018-19 time frame when 800 volts was not big in the industry. This is a beautiful picture of the Chevy Volt Gen 2 drive unit that also was born in my group. Currently, we're working on the Lunar Rover battery pack for the NASA Artemis program, and that's a pretty amazing project. So the moon is pretty crazy. So the moon and Mars, and it's a vacuum. You have minus 250 to plus 250 Fahrenheit. temperature swings and whatnot. So it's a pretty amazing project. The 6-speed transmission. So this was sort of my coming out party many years ago. This was one of those math research problems that became practically extremely useful and then hit worldwide spectacular production numbers and totally unexpected. So big deal. And then I think many symposium a couple of weeks ago, and Professor Burns, Dr. Burns, he talked about, this having this ideal transportation, each vehicle sort of custom tailored for the particular trip. And so we did something like that with this NV vehicle for the Shanghai World Expo in 2010. So this is like a Segway on two wheels with a little bubble on top. I think this you could have one or two people sitting in here. And then we found that the balancing took up so much energy, so we stuck extra wheels on it, so it started to look like this. And I think that DNA has worked its way into like the Wuling products, which are very successful, the NEVs in China. So I just put that in there, Professor Tao, because of the Burns lectures. I thought that'll get a smile from you. But if you stand back and look at sort of the clean tech problem, right? And I mentioned this in Professor Tang's class a couple of weeks ago. And I was working with Ian Sutherland from my group. He's the energy expert. And we were saying, well, look at US light duty transportation, right? We use up like 160 billion gallons of fuel every year. And if you were to put an extra $2 per gallon, you could, in theory, convert all of that to zero carbon fuel, just with clean tech methods. So 160 times 2, that's about 320 billion. Let's just round it down to 320 billion. So if we could plunk down 300 billion per year, that should pay for cleaning up, right? So that's like a big number. Hopefully we'll be able to do it with less, because if you look at this Bloomberg chart, right, it's sort of a forecasting chart. So this x-axis is time, so going out to 2050. And this is new vehicle sales worldwide, right? And we're here somewhere here. So this big green swath is electrification. This is all the BEVs. And the light and dark gray sections are sort of ICE-based, so it's ICE internal combustion engines as well as hybrid electrics. So that's all of this. And then you have PHEVs making an appearance here, and then they kind of go away after a while, right? So if you took all of that money to make clean fuel, you'd be putting it in here. So this being so big, I think that's kind of why there's such a big focus on some of the things that I'm going to talk about. So with this as background, let me leap into these three topics. So the first one, and these are actually presented in detail in papers that my group did, in the recent past. Okay, so what I've done is accepted about 5 or 6 slides from each subject area, and then we'll go deep into those, and then maybe we can pause for questions or circle back if there's time. So the first one is mixed chemistry packs. Now, it doesn't have to be mixed chemistry. It could be same chemistry, but different formats. In other words, the cell formats, one could be a power cell, one could be an energy cell. But in general, we call these mixed chemistry packs, where you're mixing and matching disparate cell types to achieve a certain objective. And we did a lot of work in that space, and I think you'll find that pretty interesting. The second one is dynamic torque modulation. So I noticed Professor Hoffman is online, so I'm sure he'd like this one. This is close to his expertise. I'm nowhere close to being an expert on this, but I think you'll see some pretty neat results in terms of applying that to product, right? So this pulsing of controlling electric motors at their optimal points using torque pulsing. It's very topical. There's a lot of literature on that. There's a lot of companies, suppliers working on that. And the last one, I brought forward megawatt charging, because I think in the last month or so, there's been any number of announcements of this or that company doing like the 5-minute charge, and we had done this some time back, and I said, hey, this is a perfect time to bring that forward. So these are the 3 topics I will present on. And let me pause and make sure you folks are hearing me. You're with me? Yep, good. I see a thumbs up. Perfect. Awesome. So I worked on these mixed chemistry packs with Shonan Shu, a very smart guy. And the work is documented in this paper here, shown down here. And I will present it in the context of electric vertical takeoff landing aircraft. The same thing would apply to heavy duty trucks. They would apply to race cars and so on. But I thought it'd be easier to have this discussion outside of the automotive context, because then it'll become pre-competitive. If I start to show you some of our vehicle parameters, then it's sort of, my boss will get kind of uncomfortable. So I didn't want to do that. But the principles are the same, right? So what happened is, like, going back to 2016, 2017, when the automotives were announcing like the targets, right, for watt hours per dollars per kilowatt hour. So automotive sort of came out and said, we see $100 a kilowatt hour happening. And when that happened, all these aerospace startups, they made a beeline to Mary Barra's door, because they were paying Eagle Pitcher and EPS and some of those specialty companies. They were paying like $1,000 a kilowatt hour for these specialty packs. And so here you come along and say you have mass production, you're going to do it for $100 kilowatt hour. This looks really attractive. And the question is, would it really work, right? Automotive packs for eVTOL. So many of you, I know this is not a new topic, so you know how an eVTOL works. If this is power versus time, you have a high power event initially where you take off, and then you cruise across town on the wing, and then another high power event where you land. And this just shows altitude, but you get the idea, right? And the reason this is a little challenging for automotive packs is because our packs are biased towards energy. So normally you'd make like 3C for 30 seconds during like a wide open throttle. These guys, the aerospace guys, they want like 10C for a takeoff, or 5C, something north of 5C. So it's definitely a challenge. So we started to work with a bunch of big and small aerospace companies, and they were pretty secretive on the aircraft design, and we were secretive about the battery design, right? And so we were kind of feeling our way around, and so we said, okay, you know what, to do this well, we'll have to design aircraft. So we started, pulled out my old notes and went into Khan Academy and looking at Bernoulli equations for uh, propellers and tip speed and so on. My younger, smarter collaborator said, let's just do AI machine learning style. So we did like scatter plots of all the existing designs that were out there, and we did best fits. So doing this, this is MTGW, which is like the aircraft mass, So this is max takeoff gross weight or something like that. MTGW. So that's the x-axis on all of these. And the big parameters, the KPIs, are hover power. So that's one. And then cruise power. So hover is takeoff, cruises go across town. And then it scales by like the size of the air. So number of passengers is a pretty good, metric for that. So we picked 3 test wells. So we picked like a 2-passenger craft, because that's what one of our partners wanted to do. Another guy wanted 4, and another person wanted 5. So we looked at these 3 test wells, and using this type of, I would say, rough estimates, we came up with, the MTGW for each of these, 1,000, 2,500, and 3,000, and the hover power, and so on. So that was to get a sort of a coarse feel for what these aircraft, what they were all about in terms of KPIs. Then the other thing to bear in mind is the cruise speed, right? Just like when you're going down the freeway in the old days, I mean, going back to like US car work, someone had written a report like 55 miles per hour is like the optimal speed. If you go slower or faster, if you go faster, you're burning up too much fuel. Just like that, for like average L to D ratios for these, the 200 kph is like an optimal speed. So that was another big KPI which we got without doing too much work. And then the other important one was the mass of the battery. So this shows a pie chart. If you look at the aircraft, about 30% is the battery, right? And I'm talking eVTOLs. 30% battery, 30% structure, and then you have a bunch of other stuff. But for us, this was the important number, 30%. So I got my MTGWs from the previous chart, and then 30% of that is what I would allocate towards batteries. The other important thing to keep in mind is when you take a cell and you discharge it sort of politely, right? It does this yellow line. So it's actually giving you full capacity. But when you abuse it and you just hit it with like 3C, 4C, or you're discharging super fast, you get like half the cell. So that's real important to keep in mind, because When you finish your trip and you're doing that last hover to land, right? That's when you're like at min SOC and you have to produce max power again. So this is definitely a challenging constraint. I'm sorry. So with this information, we were able to sort of fill out our KPI table, our table of parameters for these different designs, the 2-seater, 4-seater, 5-seater. I'll just talk about the middle one for the rest of the presentation, right? So this is a sort of a nice plot of this MTGW, or in this case, I guess this is the mass, MGTW, some people call it, but that versus range. So if you get a power cell, right, you can pick up a lot of mass, but your range is going to be small. If you get an energy cell, you're not going to have that much mass. You're not going to be able to handle enough mass. So what we did is we created this mixed chemistry system where you can say mixed energy power system. So the left side, let's say, is your energy pack. Right side is your power pack, and they're talking to each other through this DC-DC because they have different impedances, different voltages, and so on. The DC-DC is sort of like the peacemaker there. And then the load would be, your drive unit, essentially your propeller, your motor driving the propeller. So this was the basic architecture that we had. And then we did we could have gone out and sourced cells, right? So we said, hey, let's work with something that we totally understand, right? So we make energy cells as part of the Ultium products, and we also make power cells for our hybrids, right? So we said, okay, let's take our existing energy and power cells. Let's see what we can do. So we did 3 different pack designs. One with the 101 amp hour 3.5 C capable pouch cell. So that was the energy design. Then the second one was a hybrid power cell. So that's like 28 C capable, super powerful, but smaller cells, 6.8 amp hour pouches. Those went in here. And then we did the mixed design with both power and energy. And so the way we did the design is we built this tool, and just a couple of screenshots from here, but essentially it allows you to vary the series parallel arrangements for the battery packs. And for these aerospace packs, you need redundancy. You can't have like a single string, because if you lose that string, you just fall out of the sky. So you have to have forced redundancy number of the strings. But the basic structures, energy and power battery, are talking to each other through this network and through these linkages. And then you have a basic 6P, nothing fancy, 6P model for the battery pack. And there was a really nice front end where you could vary the energy string architecture and the power string architecture, and the optimizer would run through all of the different combinations and give you, the min the best solution given all of the KPI constraints we had on this table. Going back to this table, the best solution for this, meaning you come in under the pack weight, and then you go as far as you can, while also being able to take off and land. So this is the energy cell-based pack. And so here you can see the takeoff up here, that's power, then you cruise, and then you do your landing, and then you have your SOC nicely running from here to here, right? So it's full pack down to end. And we got like 163 kilowatt hours in here. Oh, but wait, if you looked at terminal voltage and if you looked at the C rate, this thing doesn't even take off. So it's like playing Monopoly, where you don't even leave the start square. You just get your $200 and you're still sitting there, because straight away on takeoff, we missed the C rate discharge limit. So this thing wouldn't work. So if I had a big red, brush, I'd put a big X on this design. So energy, thumbs down, energy cell. Power cell actually worked. So we were able to, we were able to do the takeoff, go across town, do the landing. SOC worked fine, but we didn't get very far. Given the mass constraint, right? The power cells are pretty heavy. So this is 63 kilowatt hours. So we, flew for a total of 9 minutes. So it's like a real short flight. So it's like a test flight, 30 kilometers. And the terminal voltages, C rates, etc., were fine, but this wouldn't be really useful. Now, what happened is when we did the mixed chemistry pack with the power and energy cells, you have nice takeoff, cruise across town, and nice landing. And you see for takeoff and landing, both sources of energy are providing, they're providing the power. And then what happens is during the cruise portion, the power pack gets replenished by the energy pack, right? So it's like a slow trickle charge. So it's actually at full capacity when you're doing that landing. So the power cell can sort of support the landing. So we got pretty good kilowatt hours on this, and pretty good duration, 33 minutes, 110 kilometers. So the point is, this particular design required a clever mix of the energy and power cells, which would be hard to do with a single cell unless you did a bespoke cell just for this design. And then the next aircraft guy would have a slightly different power to energy optimal ratio. So doing this kind of mixing and matching actually makes a lot of sense. Also makes sense for trucks and race cars, but I'll let you use your imagination on that, on the application. So the summary for this portion of the, for this first the first 1/3 of this presentation really is there's a lot of small font text here, but forget about that. Let's just take a look at this picture. So this is cruise range. Energy cell only, it's a 0. Power cell, you get a little bit. Mixed chemistry, you get plenty, and the packs are all the same mass. So this was a really sweet example where this would work. Now, of course, from a product development perspective, you have to work with DC-DCs and so on. And so yeah, as you're adding more and more components, you have to be sure that you can ensure their reliability, etc. But I think that was a really nice exercise. And I'm not seeing any questions in the chat. Or let me pause. Any questions, or can I keep going? Okay, I'll take that silence.
We normally hold the questions till the end.
Okay, all right. So this second section is specifically in honor of Professor Hoffman, right? As dynamic torque modulation. And this one's kind of interesting because there was a lot of supplier activity, also a lot of activity in the research community. Did you model the losses for the? Yeah, we did the DC-DC losses. Yeah. But let me circle. Let me keep going, and then I'll come back to those questions. Okay. So in DTM, let me explain DTM if you're not familiar with it. So these are motor maps. So there's a motor A and a motor B. You could think of this as, let's say, an existing 5 or 10-year-old design. Maybe this is a newer design. My colleague said I can't really talk about what's different in specific terms, but if you're a motor guy, you can use your imagination. Basically, you might be using different types of magnets, different arrangements for the magnets. You might be using different ways to excite the rotor and so on. So let's just say that this is the old motor, new motor, and you can see these are the efficiency islands, right? And you can see obviously the shape is quite different because you can, if you're a good motor design guy, you can tune these islands to actually match what you to maximize operation in the most efficient zones if you understand how your vehicle behaves. And that sort of goes back to some of the modeling tools that we have, where you can take a hypothetical vehicle and run it over cycle and look at how much time each motor spends at what speed and what torque condition, etc. So this fooling around with motor maps is like big business, right? In just getting the efficiency, max efficiency for these types of designs. Now with motors maps, there'll be this squiggly red line. Hopefully you can see it, and a blue one. Yeah, these are the best efficiency lines. So you want to do all your driving as close to these lines as possible. This is torque. This is speed. Torque, speed. Now, obviously, if the driver tips in and you need to pull very high torque, you have to get off this line, and you have to go up there and do your thing and come back. But as long as the world lets you stay on this line, you'd like to stay on this line. But what if you have to be somewhere below the line, right? So in DTM, what they do is they go on the line and then they go to zero torque, and they do that like this, So essentially, they're pulse width modulating across from this line to the zero torque line. And depending on how much you spend at zero or on that max line, you'll get a sort of a net average torque, which keeps you going. So this applies to kind of the lower torque operating regimes, which are very important for us. And you can see from these different shapes that the answer that you get in terms of efficiency improvements will be different for different motor maps. So This is DTM at a high level, and essentially the problem we were facing was taking an incumbent design and new design and comparing them and saying, should I use DTM? Number one, should I use DTM? And then which one is better, right? Which of these two motor designs is better? So that was, the framing of the problem. That was the background. And so we put these in our modeling tools. We incorporated, that is the vehicle propulsion system modeling tools. We incorporated the DTM algorithms and so on. And we drove them over the different drive cycles. So here you're seeing the city and highway cycles, right? So this is speed and torque, and this is the city cycle, and this is the highway cycle. So folks in the automotive business, you know these cycles better than I do. And then we overcycle, we looked at the drive unit loss, and this is motor A, this is motor B, city cycle, highway cycle, and this is conventional motor control, that is non-DTM, and then this is DTM. And the first round we got like no benefit for motor A, no benefit for motor B. So we're sitting around in a circle, looking at each other, looking sad, and saying, "Hey, what did we do wrong?" And Suresh Gopalkrishnan, one of our experts, power electronics, he said, "You know what? I think you're running the inverter. You're keeping it active. So if you look at the literature, they really deactivate the inverter, because if the inverter is active but your torque is zero, you're still actually burning up energy." So when we turned off the inverter, motor A actually showed benefit. 3 point, not huge, but enough, And so we're fighting for like 0.5% here and there. So this is actually pretty decent. Motor A benefited from the DTM algorithm, motor B did not. And it's just the way the islands are shaped. So then we went a step further and we looked at, so this previous thing was overcycle, right? So you have varying torques and speeds, but what if you're on the freeway? So you're looking at like a steady state. So what is the benefit at that time? So we looked at like different speeds, so 20 kph, 40, 50, and so on. Actually, the plots are for 30. But you can see actually reduction at constant speed, especially for motor A. Not much for motor B, just because of the way the islands were shaped. And so this was actually eye-opening. Though it sort of looks like a negative result, it was actually pretty eye-opening, because oftentimes we'll get questions from senior leaders saying, "Hey, I went to this trade show, I saw this thing, I think you should be doing it, or should we be doing it?" And the answer is it depends. It depends on how the motor is wound, how the islands are shaped, and so on. And we have a really nice way to model all of that and to give a definitive thumbs up or thumbs down on this technology. So Heath Hoffman, I hope you like this. And so the summary points really are more or less saying what I just said. It really depends on the design and the application and the shapes of the efficiency islands. Okay, let me check for time. So I think we're doing okay. And then let me transition now to the home stretch, the megawatt charging project. So this is something we actually executed a couple of years ago. And the background for that is like this. So here's what happened. So going back like 3 years, our bosses were looking at charging times essentially. So I have a plot here of some medium duty trucks, light duty vehicle A, B, C, D, and so on. Some of them are ours, some of them are competitors. Just looking at market information, and these blue bars are the average charging C rate. So you see a variation. Some of them are like 2.5 C. This guy's at like close to 2. This one's 1 point something, another 2, and so on. So not crazy numbers. We're talking something in the like 1 to 2 C range. And if you look at the power, right, the charging power, that's shown by these little gray bars. So this guy is doing like 550 kilowatts. These are all megawatt units. So 550 kilowatts. This one is 200, 220, so on, 210, so on. So you're looking like 200 to 500 kilowatts. And then look at the charge times. So the charge times are these teal colored, is this curve. So we're talking 10 minutes, 14 point something. These are about 14 point somethings, 11, and then I think this guy's an 8. So nothing super crazy, right? I mean, these are all pretty reasonable, but not as fast as gas. And so the bosses were saying, hey, what if you double the charge rate, right? What would it take? And we said, no, no, we can't do it. We need new cells. So we have to do a cell redesign. If you did a cell redesign, then the whole pack changes. So we have a pack architecture tool that actually lays the cells, sort of in a lateral arrangement. You can also do longitudinal arrangement. You can do all kinds of different geometric arrangements. It sort of sweeps through all the different cases. But essentially, if you change your cell design to accommodate much higher charging powers, then obviously the pack would change, how far you would go would change, etc. It comes down to like your vehicle efficiency and so on. So so after that initial, hey, no, this is going to change everything. They said, no, no, go ahead and just do the design. At least do a paper exercise and explore this. So we started to look into megawatt charging. What will it take to push like 1,000 kilowatts into a pack, into a good sized truck pack, right? So that was a big challenge. And this speaks a little bit to the pack architecture work, but I think the heart of this is the cell design, right? And in the cell design, there's a couple of different things we did. Now, I'm just showing you like two of the pathways that we followed. So this first one, I'll explain the bars in a second, but just philosophically, right? The first one is you keep the same chemistry, but you change the porosity of the electrodes, right? So you can have the ions move a little bit quicker. And that's what was done in this first design. Second one was that you change everything, change the chemistry, change whatever you need to do, just pull out all the stops. And blue is think of blue as your baseline. So that's like your incumbent cell, the existing high volume cell, and then orange is the new design where you've changed things on the electrodes. And we had to get the same pack kilowatt hours, but look, watt hours per liter dropped like crazy. Volume went up. This is the amp hours. So amp hours went up. The mass watt hours per kg was that dropped, right? And then pack mass went up. So this is intuitively obvious, but we kind of put numbers to these things. And we have a fairly intricate um, cell design tool. It's pretty good, but you can sort of vary all of these parameters and you can see what happens to the modules and when you change the thicknesses, the energy to volume ratio and so on. So there's a little bit of eye candy kind of giving you a feel for how we sweep through these designs using our tools. Now with the second design, we were able to, kilowatt hours is the same. Amp hours, we did small cells. Watt hours per liter actually went up. Watt hours per kg went up. Volume went down. So here, this was like a best of all situations. Pack mass went down. So when you're able to completely redesign, you can actually do pretty good. You can design for these types of conditions. And then once we went through sort of the paper study, we got the green signal to go ahead and do some hardware experimentation because I remember coming out of like 12 volts and 48 volts and then jumping straight into 800 volts. It was like that fear was there. Like, what are we taking on? And now that we know 800 going to this, 1500 volt systems, I think that we have the same kind of, hey, I don't know what I don't know. So we went ahead and we built a pack using, I would say, a close cousin of this type of cell. It wasn't exactly this, but it was close enough. And that is shown here. So now here, you're getting into like practical problems, gnarly problems, but I wouldn't call them super researchy, but it's definitely from an implementation standpoint, it's pretty difficult. So just getting a charger to provide like 1500 volts and 1000 amps, that took quite a lot of doing. And then the pack itself, we built it as two 800 volt sections or 750 volt sections. And initially it was to be two equal sections. Then later we did a little bit of thinking and said, do we really want 800 volts or do we want 1500 or maybe we want 1000, maybe we want 1200. So we made it super flexible. So one 800 volt section and then these two are 400 volt sections. So you could go 8 and 4 and get 12, or you could get 800 and 800 and get like a humongous 800 volt pack, or you could have a nice slim 1500 volt pack. And then we did a lot of cell testing here. You can see charge and you can see current and voltage at different C levels. We're pushing 7, 8 Cs through these cells. And this table again shows you the different pack sections. There's a pack A and B. These are 400 volt sections, and then an 800 volt pack C. When I say 400, it could be 375, 400. Not likewise when I say 800, it could be 750, 800. And then we actually went ahead and built this, right? It looks something like this. And the bottom is the big 800 volt section, top is the two 400 volt sections, and there's a whole bunch of contactors in here that allow you to switch from 800 to 1200, 1200 to 1500, and so on. And some of the switching logic is shown here. But inside, if you rip the covers off, you'd see a series of modules like this. This is what the 400 volt section looks like. And then we kept pushing higher and higher current through these systems. They initially started with just very low current, but once we were comfortable and all the sensor faults were all cleared and so on. So this was like, we had hyper safety on this because we didn't want anything to go wrong. So we had like a lot of false, false positives and so on. But once we got through all of that, you can see this plot actually shows one of the many megawatt tests that we did, charging tests. So this is time, and then you have a bunch of things on the y-axis. So this is, pack voltage starting at 1200, so real low SOC. It quickly charges up to 1500 volts, but this is the key one, the blue one. That's the power, right? You see the power build up to a full megawatt and stays at a megawatt, and then we drop it off after about 90 seconds, 2 minutes, something like that. And so this was a big deal because this was the first time we had actually pushed an entire megawatt through one of these systems at high voltage. And I bring this up because now I think in the last month, if you folks have been following a lot of the literature, I took out all of the Chinese writing here, but essentially, they're showing fast charging, right? A whole bunch of folks are showing fast charging. We like them. We work with all of them, so I didn't want to offend anybody, but but you see, they're kind of at 600 kilowatts, and then they do a quick peak, for like the thousand, the 1,000 kilowatts, and that's maybe 30 seconds. I don't know. So I think we're very comfortable. We've seen this movie before. That's the point I was trying to make. We know how to do this. And I used actually MCS connector, so that you need like two hands to hold this thing. It's big and heavy. But there's different ways to do it, I think. So that was very interesting. It was very cool. We're no longer scared of 1500 volts. That's the big takeaway, and we know how to do this. And with that, I'm sorry, what did I do? Yeah. So with that, that brings us to the end of my presentation. I'm happy to take questions. I hope you found this interesting.
Well, thanks so much, Madhu. The interesting coincidence is we were recently asked by the state to find synergies between aero batteries and vehicle batteries, and you've given me the story I need to use now, so that's fantastic. I'll turn it over to Jamie because we do have some questions in the chat.
Yeah, Madhu, great job. You can stop sharing if you want so we can see you as your answer. We have a few questions in the chat. One was, did you model the losses for the DC-DC converter?
Yes, we did. Yes, we did.
All right, good. And then a follow-up from Heath Hoffman, our drives lead here at U of M in the EV Center. To clarify your comments at the end of the hybrid pack configuration section, did each pack have its own DC to DC converter that interfaced it with the bus in your study? And if so, was there a power management system that allocated power requests to the different packs?
No, there was the DC to DC converter was only on one side, and so it wasn't both. And yeah, there was a power management system.
Good. You'll like this one. This is from Daniel Kumi. He says, my company, Smart Energy, has developed a novel material for passive thermal management of batteries for space application that can help maintain battery stability under extreme space conditions, including cryogenic temperatures on the lunar surface. Would you be interested in collaborating with us for this rover project?
Absolutely.
Good answer.
Madhu, what is the best way to make that connection? Are you willing for us to share your your GMID?
Yeah,
Email ID?
but it's just madhu.raghavan@gm.com. How's that?
Thank you.
Great. Happy to facilitate that connection. Solomon asks, what is the main issue with fast charging? Is it thermal? Does state-of-the-art fast charging use passive liquid cooling?
Thermal's a big part of it. I think lithium plating is the other part of it. Those are the two. And then state of the art for that kind of fast charging, we do active cooling. Actually, it's not passive. I think we had overcooled the system. We didn't want any trouble. So there was like Niagara Falls going through the pack. Actually.
Great.
But excuse me, was it immersion or was it still
No.
conduction?
No.
Okay, just checking. Thanks.
And then Harry Husted asks, what was the kilowatt sizing of the DC to DC converter? It looks like it can be lower than the hover power.
Yeah, very smart question. Yeah, you don't want to see. So if you size it so all the power is going through the DC-DC, then essentially the benefits of doing this you have lost because you have so much parasitic mass from the DC-DC. So you want to do differential DC-DCs. That is just the difference in the power is what you want to manage between the energy pack and the power pack.
Great. And then there's another question. Do power electronics also require modification in the thermal management with fast charging? Or is it mostly the batteries that need the thermal management?
I didn't see any big standout challenges on the power electronics side. It was the cells.
Okay. And then George asks, what is the thought process when building the foundation around power first? The way I see it, it's all about phase change and thermal dissipation. Is this forcing a shift from DLC to possibly phase change cooling system, similar to that of what we see in thermal generators? Mixing thermal management with regeneration capabilities?
Yeah, phase change is super important. Yep. So what happens with the PCMs is there'll usually be like a cost threshold, and the more stuff you add in there, you're fighting that cost battle. So if we can do it without PCM, that's great. But I've used PCM, and the thing is, the bus bars on our megawatt pack were so generously proportioned that thermal on the bus bars was not a problem. It was mainly on the cells that we were worried about. So I ended up not doing much with PCM there.
Okay. Ali asks, if we manage to successfully achieve mass megawatt charging stations, what impact would that have on the distribution grid? Is there any study on this aspect?
Yep, I'd have to. So Professor Chu was at U of M a few weeks ago, and he talked about the distribution grid and the impact, especially in certain regions like California, where they have a very significant duck curve, I think. And I think it's regional. The impact on the distribution grid would be regional. So I've seen studies that suggest that initially you won't have this huge impact, but if there's enough adoption, yeah, you will have some. And I'd have to get back to you on that. I don't have the facts on my fingertips. Yeah.
Okay. Another question is, what kind of chemistry is used when temperatures are too low, like in the Lunar Rover project?
So you're putting me in a it's a competitive. You're backing me into a corner on that.
You can
Don't
choose
feel
to
pressure to
you
answer.
can choose to pass on the question.
Yeah.
Yeah, I'm sorry. I have to.
No
pass on that
pressure.
one. Yeah.
So the last one here in the chat right now is thank you for the great presentation. You didn't talk much about battery aging. Since recent real-world data shows battery aging isn't as scary as we feared, is it time to loosen BMS limits on SOC range and thermal management to tap into more performance?
So that's pretty interesting. It actually varies by user. So if you could actually fine tune that, because certain people drive in a certain way that they beat up on the pack a lot more, just like cell phone users, right? How one person might use it is different from how another person might use it. So I think if you can get sort of real-time information on state of health, I think you can get more out of the packs. Yes, very good idea. Yeah.
Great. Well, that was the end of the questions. Alan, do you
Yeah.
want to take it over?
So, first, Madhu, you lived up to well, at least my expectation, which I assume means everyone. So let's all thank you for a fantastic presentation with as much virtual applause as we can get. The other thing is, this has been a series of what we're calling our surge webinars. Jamie had to come up with something that implied electric flow. And the plan is to continue these monthly. If you have not yet become an affiliate of the EVC, it takes nothing to do that, but go to our website and sign up. That makes you informed of our various activities. And stay tuned for the next set of webinars. But again, Madhu, I still take some pride in having worked with you for so long. So thanks for a fantastic job.
Thank you. And Alan, you've been a mentor over the years. I have no problem acknowledging that and thanking you for it. So this is the least I could do in return.
Oh, I'm going to cash in a lot more than this. So thanks, everybody. I hope you are getting ready for what's supposed to be reasonable weather this weekend as we welcome spring. And stay tuned. If you're not watching us on LinkedIn, if you're not regularly going to our website, it's really we have moved from the planning stage to the operational and doing stage of projects, education, workforce, and technology. So thanks everybody for joining us.
Thank you.